Hello and welcome to Control System Engineering lecture series. In this lecture, I will discuss Linear and Time-Invariant Systems or LTI. LTI is a title given to a class of systems that respond in a certain way when subjected to an arbitrary input. LTI systems have the following defining properties. Number one, homogeneity. Number two, superposition, which is also referred to additivity. And the third one is the time invariance. You might not be too familiar with any or all of those words, but don't let that discourage you because the concepts of LTI is actually very simple. I will provide a mathematical description of each and show an approach on how we can use these properties. Let's start with the two criteria, that is homogeneity and superposition, that describe the linearity. Homogeneity. Let us consider a system that is represented here in the form of a block. When you subjected an input x of t, it produces an output y of t. Homogeneity states that if you scale the input by a factor a is any value, random value, then the output would also be scaled by the same factor. For example, if you double the input, output would be double. Simply, we can say that it will scale your input. If you scale your input, your output will also be scaled. If we are going to describe these things graphically, let us consider a graph which represents the input and the other one which shows the output. Graphically, we can see that for this system, if the input is a step function of magnitude 1, the output happens to be a sinusoidal with the amplitude 1. Likewise, if we double the amplitude of the step function, the output would also be double to amplitude 2 as represented in the graph. Now, superposition. For superposition, let us consider a multiple systems. In the first system, if we apply x1 of t as an input, you will get y1 of t as the output. For the second system, if x2 of t is the input, it produces output y2 of t. Now, according to the superposition, if we add the two inputs together, for example, if we are going to add these two systems, it will result x1 of t plus x2 of t that produces the output y1 of t plus y2 of t. This simply add up the things. The time invariant system, if there is a shift in the time, it also reflects in the output. For example, if there is a shift in the input A, you will see the shift in the output also. These three, homogeneity, superposition, and time invariance restrictions are all that need to be met in order to have an LTI system. However, these restrictions are very much severe. Severe in a sense, in a fact that particularly no real world system fully meets these conditions. The question is why LTI systems are important. According to the Richard Feynman, we can solve them. LTI systems are important because we can solve them. We can only solve very simple and contrived non-LTI system, but equally important to being able to solve them in that a wide range of physical systems can be approximately very accurately by a LTI model. In order to understand this, let us consider a mass m. When we apply a force F on it, it moves a certain distance with some velocity. The force applied to a mass is such that you are applying an impulse into a system. After this, you will observe the response of the system. You might look something like that. The full response of the system would just be the summation of all the signals. If we apply force F again, it will result in this form. If we double the force on the mass m, you will see the double magnitude or amplitude in the output graph. Response to a system would just be the summation of all these signals. In this case, the thick line shows the sum of all the signals. This method works easily with one or two impulses, but if we have an input to a system that wasn't just made up of one or two discrete impulses, let us consider ramp function. That is further break into series of sequential impulses. With an LTI system, we can say that the output is a summation of the responses to each of them individual impulses. Now, to understand this, I drew these impulses very discreetly in practice. Each of these impulses would be infinitely close to each other. When we're going to draw the response of each impulse, it will look like that. When you do this summation in the time domain, this is called convolution, which can be very difficult. However, if we first transform the impulse response and the input signal to the S domain using Laplace transform, the convolution becomes the multiplication. This is basically the basics behind the transfer function. S domain can only apply to the LTI systems. So how can we take advantage of this knowledge? As a control engineer, you will be responsible for designing the controller, but you might also be responsible for choosing control systems element. For all this, you must choose the control element that are close enough to being LTI that have non-LTI behavior. Let me leave you with a common example of a non-linear spring. If you plot a real spring stretch length versus its restoring force, it would be most likely having a shape similar to this. When you stretch it too far, eventually the material will start deforming. If you compress it too far, the coil will start bunching up, physical impact occurs. We select somewhere in between, and what can be considered the operating region of the spring is that there will be a nice nearly linear relationship between the force and the distance you were selecting a spring for your design. Hopefully you have a better understanding of what an LTI system is and why they are so important to design a control system. Thank you very much.